All right, so have you ever heard that saying, successful systems all work alike, but each failing system has its own problems?
Yeah, I think I have. Sounds familiar.
Well, a recent paper actually used that line, and it resonated with me.
Interesting.
Yeah, it made me think about how, there's often a clear path to success.
Right, like a recipe or a formula.
Exactly. But when things go wrong, well, there could be tons of reasons why. And that, believe it or not, brings us to today's deep dive. Multi-agent systems, or MAS for short, powered by those impressive LLMs, large language models.
Ah, yes, LLMs. The potential in this area was initially so exciting. I mean, just the idea of having multiple AI agents working together like a team to tackle complex tasks.
Right, like a dream team of AI.
Exactly. You'd think combining all that LLM power would lead to, some huge advancements compared to just a single AI working alone.
Yeah, you'd think so, right? Like this super efficient AI team just crushing it. But that's not quite what's happening, at least not yet.
No, not quite.
This research actually found that when these systems are tested using standard benchmarks, their performance is, well, it's kind of underwhelming compared to what single agent systems can do.
Hmm.
Yeah, and I bet you're wondering, just like I was, why are these collaborations, these seemingly intelligent collaborations, why are they falling short?
It is a bit of a head scratcher.
It is. And look, I know you're here on the deep dive because you value understanding complex stuff quickly and without all the fluff.
Cutting to the chase.
Yeah. So our goal today is to give you that clear path to understanding the core challenges in this whole multi-agent LLM world. And don't worry, we're going to keep it digestible, no overwhelming jargon.
Absolutely.
The sources you sent over really dig into this paradox.
Right. One study in particular really caught my eye. They actually analyzed a bunch of existing MAS frameworks.
Oh, wow.
Yeah, and they identified specific points where these systems tend to break down.
So they didn't just theorize, they actually got into the nitty-gritty of how these things work, or don't work, I guess. And what's fascinating is they didn't just find a couple of issues. This study uncovered a whole bunch, 14 distinct ways these systems can fail, and they've nicely categorized them into three main areas.
A whole taxonomy of failures.
Yeah. Consider us your guides as we navigate through it all. I'll be here to break things down in a way that everyone can understand and
And I'll chime in to provide more context and analysis,
Mhm.
helping you grasp the bigger picture of how these findings fit into the world of AI research.
So this whole idea of multi-agent systems, with all their potential, the reality is their performance, it leaves a lot to be desired.
That's one way to put it.
The paper actually states that their performance on benchmarks is minimal compared to single-agent frameworks.
Ouch.
Yeah. And they even looked at the correctness rates of some leading open source MAS, like ChatDev, for example. Figure 1 in the paper, it shows that its correctness can be as low as 25%, with even advanced models like GPT-4o and Claude 3.
Wow.
It's not just a small difference, it's a huge gap.
Yeah, a pretty stark contrast.
Okay, so before we get too deep into this, it's probably a good idea to make sure we're all on the same page about what we mean when we say LLM-based agent and multi-agent system.
Right, terminology is key.
The paper gives a nice, clear breakdown of these terms. So an LLM-based agent, think of it like it starts with a set of instructions in its prompt. And then, as it goes through conversations, it builds up a history, like a memory of sorts.
Right.
But here's the crucial part. It can actually interact with its environment, like using tools and stuff to complete tasks.
Well, it's not just passively processing information.
Exactly.
It has some agency in the digital world.
Precisely. It's like it has a role to play, a memory of its past conversations, and it can actually get things done in the digital world.
Exactly. Now, a multi-agent system, as you might guess, it's basically a bunch of these individual agents all working together.
Okay.
And they're designed to interact with each other within some kind of organized structure. The goal, ideally, is to achieve what the paper calls collective intelligence.
Ah, so like the whole is greater than the sum of its parts kind of thing.
You got it. And the reasons for building these systems, well, they sound pretty good in theory. I mean, the idea is to break down big, complex tasks into smaller, more manageable ones.
Makes sense.
And then you can work on different parts of the problem at the same time, keep different tasks separate, and maybe even use the unique strengths of different models.
Right.
Plus, you can get some diverse reasoning going on with agents, discussing and giving each other feedback.
So all these potential advantages, it really does sound promising.
It does, doesn't it?
So where did things go wrong? That's where this really cool study comes in, the one that's forming the basis for our deep dive today. Instead of just guessing why MAS systems fail, the researchers did a super thorough evaluation.
Right.
They looked at 5 popular open source MAS frameworks. And get this, they tested them on over 150 different tasks.
Wow.
Yeah. And they had 6 expert human annotators carefully examine the interactions between all these
There's
agents.
a really impressive level of detail.
It is. Now, the methodology they used, it's worth highlighting because it's super rigorous. They used something called grounded theory, which basically means building understanding from the data itself.
Right, not starting with some preconceived notions.
Exactly. They kept analyzing and refining their understanding of how these systems could fail. And to make sure their findings were solid, they had 3 independent experts review some of the data.
Hmm.
And get this, they got a Cohen's kappa score of 0.88.
Okay, now for those who might not be statistics whizzes,
Yeah.
that score basically means there was a really strong agreement between these reviewers.
Ah, so it's not just random observations, but actual consistent issues.
Exactly.
So they called their findings the multi-agent system failure taxonomy, MSFT for short.
Catcher?
Right. It's like a categorized list of all the ways these AI systems can mess up. Remember those 14 failure modes we talked about?
Right.
They grouped them into 3 main categories.
Makes sense.
And figure 2 in the paper visually shows how it's all structured. The first category is specification and system design failures. This one's a biggie. It accounted for something like 37% of the problems.
Yeah, a significant portion.
And the interesting thing about these failures is they often come from, like, the very blueprint of the MAS. It could be flaws in the overall design, how conversations between agents are managed, tasks that aren't clear enough, or even problems with the specific roles each agent is assigned.
Right.
And the paper gives some super clear examples, which I always appreciate.
Yeah, examples really help make these abstract concepts more concrete.
Absolutely. So one failure mode they highlighted is called disobey task specification. And this happened in over 15% of the cases they looked at. Like, for example, they found this case with ChatDev where it was told to create a 2-player chess game, right?
Okay.
And it was supposed to use standard algebraic notation for the moves, like, key 8 or QD4, the way you'd see it in chess books.
Yeah, the standard notation.
Right. But instead, the system made a game that used numerical coordinates, like, by 1, y1 to by 2, y2.
Oh, wow. So it basically ignored a key requirement.
Yeah, completely missed the mark. It's like technically it created an output, but it didn't do what it was asked to do.
Exactly. And that's a common theme we see with these failures. It's not always about a complete lack of capability, but rather a misalignment between what we intend the system to do and what it actually ends up doing.
Right, like a disconnect somewhere.
Exactly. Another related failure mode, they call it disobey role specification. It showed up in about 5.5% of cases. Here, an agent basically does stuff it's not supposed to be doing, right? Going beyond its defined role.
Ah, like stepping on someone else's toes.
Exactly. The paper gives an example of ChatDev's chief product officer agent. During this demand analysis phase of a project, it starts acting more like the CEO.
Uh-oh.
Yeah, it's making decisions about the overall product vision instead of focusing on analyzing market demand, which is what it was supposed to be doing.
Oh, I see. So just like in a human team, if someone starts taking on tasks they're not supposed to, it can mess things up.
Precisely. It reinforces the idea that it's not enough to just have really smart agents. We have to carefully define their roles and make sure they stick to them.
Right. Clear boundaries and responsibilities. Makes sense. All right, so moving on to the second category, inter-agent misalignment. This one accounted for roughly 31% of the failures.
Yeah.
This is all about the challenges these agents have in working together effectively.
So the teamwork aspect.
Exactly. These failures are about communication breakdowns, problems with collaboration, conflicts between agents, or even just the task kind of going off track. And within this category, they found several specific failure modes. Like one interesting one is conversation reset, where the dialogue between agents, it just randomly restarts.
Oh, wow.
And this happened in about 6% of the cases. So imagine you're working on a problem with someone, and every few minutes, they completely forget what you've talked about and want to start over.
That would be incredibly frustrating.
Right. It's like hitting the reset button over and over again.
Yeah, not very productive.
Not at all. Then there's fail to ask for clarification, which surprisingly is something these agents struggle with sometimes. It happened in a bit over 2% of the cases. So if an agent comes across something confusing or unclear, you'd think it would ask for more info, right?
Makes sense.
But sometimes they just keep going without seeking clarification, which obviously can lead to mistakes.
Yeah, assumptions can be dangerous.
Exactly. And then you have task derailment, where the agents lose sight of the goal and go off on tangents, which happen in 5.5% of the cases.
Ah, getting sidetracked.
Yeah. But maybe even more problematic is information withholding, which accounted for over 9% of the failures. This is where an agent has info that other agents need, but it doesn't share it.
Oh, wow.
Figure 5 in the paper shows a good example of this. A phone agent doesn't tell the supervisor the correct username requirements, which leads to a bunch of errors.
Ah, so like in a human team, where if someone keeps vital information to themselves, it can really hinder the progress.
Exactly. It's like having a teammate who knows a crucial piece of the puzzle but keeps it a secret. Then there's ignored other agents' input, which occurred in about 8.6% of cases. This is where an agent basically ignores suggestions or even corrects solutions offered by other agents.
Hmm.
The paper gives an example in Appendix D.1 of this happening in a multi-agent peer review scenario. One agent suggests a correct solution, but it's ignored.
So, despite having access to the right answer, the system still fails because of poor communication and collaboration.
Exactly. It's like your teammate gives you a great idea, but you just dismiss it. And lastly, in this interagent misalignment category, there's reasoning action mismatch. This happens when an agent's logic and its actions don't match up. It occurred in just under 5% of the cases. Appendix D10 gives an example of hyperagent working on a pilot bug. The navigator agent figures out the problem, but then it suggests a less effective solution to the planner agent.
Interesting. So, the agent understands the issue, but it can't translate that understanding into the right course of action.
Yeah, disconnect between thinking and doing.
Precisely.
Okay, now for the third and final category. This one's called task verification and termination. And it's just as common as interagent misalignment, accounting for about 31% of the failures. This category is all about how these systems wrap up their work and whether the results are actually good.
Okay. So it's not enough to just go through the motions. You have to make sure you're actually producing something valuable and accurate.
Exactly. It covers situations where the system stops too early, doesn't properly check its work, or uses faulty verification methods. One key failure mode here is premature termination. The agents end their interactions before the task is actually finished.
Cutting corners, huh?
Yeah, it happened in about 6.5% of the cases. Appendix D Type 13 has a good example of this with HyperAgent working on a Flask bug. The editor agent says it's made a fix, but it actually hasn't, which leads to the whole thing failing later on.
So it's like declaring victory before the battle is truly won.
Yes, it's like ending a project halfway through and saying it's done. Now, another big one here is no or incomplete verification. Over 13.5% of the failures were because of this. Basically, the system either doesn't check its work at all or it does a really poor job of it.
Oh boy.
The paper has examples of this with AG2 messing up math problems and MetaGPT not properly checking if its chess program follows all the rules.
Mm.
And then there's incorrect verification, which happened in over 2% of the cases. This is when the system tries to check its work, but the checking method itself is wrong, so it thinks an incorrect answer is actually correct.
A flawed validation process.
Yeah, like a broken measuring stick.
Hmm.
So when you look at all these different ways these systems can fail, it's clear that building effective multi-agent systems is a lot harder than just putting a bunch of smart LLMs together.
Absolutely.
And the paper actually goes beyond blaming these failures solely on the limitations of the LLMs.
Oh, interesting.
They argue that a lot of these problems come from organizational design flaws within the MAS frameworks themselves.
That's a fascinating angle. So it's not just about the individual AI components, but how they're structured and organized to work together.
Exactly. They compare these AI failures to, get this, failures in human organizations.
I see where they're going with this.
Yeah.
It makes sense, actually. Even with talented individuals, a poorly structured team will struggle.
Precisely. They even reference work on high reliability organizations like, air traffic control, nuclear power plants, places where even small mistakes can have huge consequences.
Right, those systems where precision and coordination are absolutely critical.
Yeah. And what's really cool is they found specific links between their taxonomy of AI failures and characteristics of high reliability organizations.
Oh, so like real-world parallels.
Yeah,
Yeah.
they connected disobey role specification to a characteristic called extreme hierarchical differentiation,
Yeah.
which basically means having super clear roles and responsibilities. And they also link fail to ask for clarification to something called deference to expertise, which is all about recognizing and respecting expertise within a team or organization.
So they're suggesting that we can learn from how effective human organizations are structured to build better AI systems.
Exactly. It's like the decades of research into how to make human teams work well might be the key to more robust and reliable AI teams. Now, the researchers didn't just focus on the problems, they also explored possible solutions, both tactical approaches and more fundamental structural strategies.
Okay, so let's start with the tactical approaches. What are those about?
Well, these are like more straightforward adjustments to how these systems are set up, like improving the prompts given to agents, making their roles and tasks super clear, encouraging them to double check their work, and defining better communication patterns.
Right, so fine-tuning and refining the existing framework.
Exactly. They also looked at enhancing the way agents are coordinated.
The orchestration, so to speak.
Yeah, maybe using more modular agents or having different agents check each other's work.
A system of checks and balances.
Yes. And they actually tested some of these tactical approaches with two existing multi-agent frameworks, AG2 and ChatDev. What they found was it's kind of mixed. Like, for example, with AG2, in a math chat scenario, refining the prompts did improve performance.
Hmm.
Yeah, it worked with both the GPT-4 and the GPT-4 models.
Okay, so there's some potential there.
Right. And they also tried a new agent structure with specialized roles, and that improved things too, but only with GPT-4o. So what works with one model might not work with another.
Right, so the effectiveness of these tactical tweaks seems to depend on the underlying capabilities of the specific LLM.
Exactly. Now, with ChatDev, they tried refining the prompts to enforce a stricter hierarchy, and they also made a more significant change to the framework's overall structure, moving from a directed acyclic graph to a cyclic graph, which basically allows for more back and forth and refinement.
Hmm.
They tested these changes on a couple of benchmarks, and while they did see some improvement, it wasn't huge, like only about a 14% increase in task completion.
So it's an improvement, but not a groundbreaking solution.
Yeah, it seems like these tactical approaches are more like bandages than cures. They help a bit, but they don't solve the core issues. That brings us to the structural strategies that the researchers talked about.
Okay, these sound more like addressing the root causes.
Exactly. These are about changing the fundamental design and operational principles of these systems. And one of the most important things they highlighted is the need for stronger verification methods.
Right, because if you can't reliably verify the work being done, the whole system becomes unreliable.
Exactly. Like they said, automatically generating unit tests can help in some areas like software engineering, but there's no universal way to guarantee the correctness of outputs across different tasks.
Yeah, that's a tough nut to crack.
It is. They also talked about how important it is to have standardized communication protocols between agents.
Ah, so instead of just having agents communicate in free-form natural language, which can be ambiguous, they're suggesting more formal and structured communication.
Right. Clear intentions, defined formats, things like that. It's like establishing clear communication guidelines in a human team.
Makes perfect sense. Minimizing the chance of misinterpretations and errors.
Exactly. What else did they suggest?
Well, another interesting idea they brought up is incorporating something called uncertainty quantification.
Okay, that sounds kind of complex.
It is a bit technical, but essentially it means giving agents the ability to say how confident they are in their reasoning and outputs. Like maybe an agent would only take action if it's above a certain confidence level. If not, it could gather more info or check with other agents.
So it's like knowing when to ask for help or double check things.
Exactly. And they also emphasize the importance of memory and state management.
Right, because if the agents can't remember what's happened or what the current state of the task is, it's going to be chaos.
Precisely. And managing memory and state becomes even harder in multi-agent systems because now you have multiple agents interacting over extended periods.
Yeah, keeping everyone on the same page, so to speak.
Exactly. And finally, they mentioned using reinforcement learning to train agents to behave better and align their actions with their roles and the overall goals.
So like training the AI team to work together more effectively.
You got it.
So it sounds like building better multi-agent systems is about taking a more strategic approach to their design. It's about robust communication, effective verification, and learning from how successful human organizations operate.
Absolutely. And the paper really drives home the point that simply making the individual LLM smarter, it's not enough.
Right, it's about the whole team, not just the individual players.
Precisely. We need to think more carefully about how these AI teams are structured and how they communicate.
Okay, so to wrap things up, what we've learned today is that building effective multi-agent LLM systems is way more challenging than it might seem at first glance. It's not just about throwing a bunch of smart AIs together and hoping for the best. This MSFT taxonomy that the researchers created, it's a really valuable tool for understanding all the ways these systems can fail. And for you, dear listener, I think the takeaway is that building successful AI systems, especially these collaborative ones, it actually has a lot in common with building successful human teams.
And for those of you, like our dedicated listeners who want to dive deeper, the researchers actually made their entire data set and their LLM annotation tool public.
Oh, cool.
Yeah. So if you're interested in exploring this stuff further, you can actually get hands-on and see how it all works.
That's fantastic. It's a great reminder that while LLMs are super impressive, creating truly effective AI systems, it's about more than just individual intelligence. It's about building a well-structured, well-coordinated team.
Couldn't have said it better myself.
Well, on that note, we'll wrap things up here. Thanks for joining us for another deep dive, and until next time, keep those brains buzzing.
And those AI agents collaborating.